Okay,
ja imam problem, ne mogu da startujem kameru. Ovim poruku, you can't start your video because the host has stopped it.
Sad ću ja to dati.
Ne znam, to može naknadno, čekaj, vidim kako to ide. Okay, people, we are going to start in a few minutes. I'm glad that I already see more than almost 30 participants here attending to this first Quantum Serbia meetup in 2021. First of all, I would like to say, I would like to congratulate all of you and wish happy holidays that was passed before this. And as I might see, there is a few people with non ex-Yugoslavian names here. So basically, I think that we should be we should be presenting in English, like, so that's the information for sure. Our next speaker is going to be Saša Lazarević, who is IBM Quantum ambassador and Qiskit Advocate. Beside that, he's also a part of our core team, let's say our small group that is running this Quantum Serbia ecosystem so far. And he's the one, I think that you're the first person that we contact outside of initiative to see what is happening right now in the quantum, and we get a lot of helpful insights that help us to start this Quantum Serbia ecosystem. So without further delay, I would like to give the word to Saša, who will tell us more about himself and to the topic of this meetup.
Okay, thank you, Aleksandar. Hvala, Aleksandre. Srećna Nova godina svima. Happy New Year to everybody. All the best in 2021 from my side as well. Well, my name is Saša Lazarević. I'm originally from Serbia, from town called Zvečan in our province, Kosovo and Metohija. So I studied and graduated IT from Faculty of Organizational Sciences at University of Belgrade. And I've lived since last 22 years in Switzerland, most of the time that I worked at IBM company in different roles. And since 2-3 years approximately, I've been involved also in different activities and projects around quantum computing within IBM. So I don't have a background in physics, as you have noticed. And probably you are wondering, okay, well, do we need to have a background in physics in order to understand and practice quantum computing? Well, I'm going to talk also about that a little bit during this presentation, this event. So please follow this. It will be interesting. This is the third time actually that I'm talking about quantum computing in front of Serbian audience, or in Serbia. The first time it was November 2018 within a AI conference that took place in Novi Sad, International AI Conference. So I was talking about AI tools from IBM, but then I gave a brief introduction to quantum computing, and I invited all young people in Serbia to pay attention to quantum computing and to start learning early enough. Because if you start early, it's like investing in Bitcoin. So you can imagine if you were there when Bitcoin was $100, how much benefit you would have now. So it's the same with new technologies. Who is early there, he or she can make exponential growth and benefits. Second time, it was the end of 2019. I'm grateful to Professors Aleksandar Akićević and Ana Poledica from Faculty of Organizational Sciences, that we organized an event. We invited also people from academia, from other schools, and the idea was actually that we start some interdisciplinary discussion, conversation around quantum computing, what it means, and how Serbia can catch up with other more developed nations. And now, the third time, this is a really great follow-up on all these things that we had previously, that I see that basically this is a very interesting community, bringing together professionals, data scientists, computer scientists, businessmen, experience with launching startup businesses, but also people from universities, and also all interested individuals. So I think this is great continuation. Especially, I'm happy to see people from outside of Serbia who are not originally Serbian joining this, because only through international collaboration, any country in the world can actually develop this very difficult and very advanced technology. So I have an introduction to this subject, and then I will also go through my standard slides that we have at IBM. I'm talking in English, but for those who have difficulties to understand some of the terminology, please use the chat to ask questions in Serbian, and then I will stop and help you understand. I will answer that in Serbian, so that we have we make sure that everybody is able to follow this talk. So let me share my mind map. This is how I'm going to begin. Okay. Yeah,
it's still not shared.
It's here. So it's the introduction into quantum computing that will help everybody to bring everybody on the same page now, what we are talking about. History of quantum computing. So it has long history, basically. So already more than 100 years that some very distinguished scientists have discovered quantum phenomena, important also for quantum computing that we are using nowadays in quantum computers, like superposition, entanglement, interference. Well, probably you have learned a little bit about that during your high school or university studies. These phenomena was very difficult to understand why they are happening, and still science doesn't provide really a clear answer why these things are happening. But scientists, together with mathematicians, so they have developed a mathematical framework to explain how these phenomena are taking place. And that is actually what we call quantum mechanics. So quantum mechanics is not some mechanics like that we have in the physical world, but it is a mathematical framework that helps us understand how these things work. It is based on linear algebra. It is complicated. It is complicated, actually, to understand and to learn. It takes time. And probably you would wonder whether you really need it if you want really to learn about quantum algorithms, if you want to code different problems on quantum computers. So the answer is actually, if you stay on the high level, if you know optimization, your own optimization problem, you work in finance or in logistics, and you know how to code your original problem on traditional computers. And if you just want to use the libraries already developed by someone else, so in that case, I would say, well, you would probably not need really a lot from this quantum mechanics. You would need to understand what it means to use quantum gates, what they are, and so that you can adjust your quantum algorithms. But most of the time you would just deal on very high level. So that is true. So in that case, we would say, well, you need just a very superficial knowledge of quantum mechanics. However, if you want to adapt these quantum algorithms or to innovate in this field, which will be important because currently while we are talking here, so there is in a lot of different countries, really a lot of young people learning, coding, testing, studying quantum algorithms. So you will see that there is a lot of competition there in the field, in the market. So in that case, if you want to go deeper, then the level of knowledge that you need to have from quantum mechanics will be higher. Especially if you want to adapt your quantum algorithms to run on different kind of hardware, or if you have a new problem that you want to resolve in an innovative way, you would need to understand that, well, okay, how do I represent this problem in a quantum way? What is the underlying Hamiltonian that I need to define? Then how do I translate this quantum, my problem Hamiltonian, into qubit Hamiltonian? And how do I run this on a quantum hardware? So in that case, well, the level of knowledge that you will need from this quantum mechanics will be higher. So how to learn it? I mean, of course, if you're at the university, if you go to physics, then, well, that's ideal. So you have teachers, you have professors, you have books, you have time to spend on that. So you can ask questions and you can learn, really progress very fast. But if you don't have time for that, I mean, to study, go back to the university, then probably you will look for some good books and you will look also for some online courses. Luckily, there is quite a lot of stuff available, how to learn about quantum mechanics as well, especially for computer science people. And you can find it online. There are really lately, the last few years, there are more and more online courses about it. But that is also, I see as the opportunity for our universities in Serbia and other universities in the world to develop a program dedicated for computer scientists or for people who are not really, I mean, that don't have a background and don't need really a deep and comprehensive knowledge from quantum mechanics. A subset needed only for the people to understand how to progress with quantum computing. So that is the opportunity that I see immediately, I can say now, for developing dedicated courses in this field. So it started more than 100 years ago. It was explained with quantum mechanics, but then starting from 1980s, there were people who were saying, well, okay, well, this quantum phenomena can be used actually for computation to simulate some systems in physics, or even more than that. And there were very interesting algorithms that appeared during this time. For example, the Shor's algorithm that demonstrated that encryption, public and private keys, they could be broken simply by an algorithm running on quantum computer. And this created a lot of interest in the scientific and professional community, also among the companies, but mostly from governments who said, well, okay, but then in that case, this is risk for us, and this is potentially very interesting for us to use it in order to, well, see what the others are doing, what the others are talking about. So it created a lot of, similarly, a lot of investment in this field already at that time. And then starting from 1997, there was a first quantum computer. It was based on nuclear magnetic resonance, created by 3 research labs in the world, in California, IBM, and also in the UK, Oxford. But this technology didn't really allow to perform entanglement between multiple qubits. So in 1999, there was a research paper from a Japanese scientist who started talking about superconducting qubits, and then IBM said, well, we are specialists in superconducting technology, so we can use it also for quantum computers. So at that time, IBM started really investing time and efforts into this field. Well, in the beginning, it was just reserved for the researchers. It was not really of any practical use, but from 2017, IBM just made available to the broad audience, to all people who would like to use it, a first quantum computer with 5 qubits. And it is free, so everybody can test, learn, develop quantum algorithms on small quantum computers. So if you just search IBM quantum computing, you will be able very easily to find this circuit composer, where very visually you can just compose a circuit based on quantum gates and test it, run it directly on a quantum computer. IBM currently has 29 machines. Those larger machines, they are reserved for those organizations who pay the membership. But still, 5 qubit machines and 1 machine with 15 qubits is also available to people who just register their account. So this period where we are developing quantum computers is called NISQ era. Why? Because these computers, they are still too small to be able to run real quantum algorithms that we would like to have. So these computers currently, they have 50, 60, 70 qubits. The forecast is that within several years, 3 to 5 years, we will have more and more qubits that will allow implementation of some practical cases where quantum computers will provide the advantage comparing to traditional computers, including supercomputers. There were also the news about quantum supremacy, or if you like, if you don't like this word supremacy, I mean, you can just say superiority, quantum superiority, first by Google, it was November 2019, then also recently by Chinese group of researchers. So what they have done is of no practical use. They managed to create data based on a particular probability distribution that can't be simulated with traditional or classical computers. So now, what do we do with this distribution? Well, we can't do really much. So we would like to see implementation of a real case, real problems, real world problems. And that is where the community, now professional community, researchers are working currently on. With larger computers, as I have said, the forecast is within next 3 to 5 years, this will be possible. So I mentioned here hybrid computing. Well, that is basically the mechanism how quantum computers can provide this quantum advantage. It means that particular routines can be run on a quantum computer, and then their output will be taken, and we just process this output on a classical computer. In case of optimizations, we adjust and optimize the results that we got from a quantum computer, and then adjusted output is again brought back to the quantum computer. So we do this iteration multiple times, and that is the basic principle how hybrid computing will work in the near future. So the big goal is actually to create fault-tolerant quantum computers with thousands of qubits of high quality. And when we are talking, for example, about this non-Shor algorithm that can break encryption, well, for that, we need fault-tolerant quantum computers. Currently, quantum computers don't have a coherent state for very long time. And the algorithms, the real algorithms that we, quantum algorithms that we would like to use for optimization, for example, or I'm talking about Shor's algorithm, but in this case, it would require deep circuits. It means hundreds, if not thousands, of gates, of instructions in a sequence. So the quantum computer would need to keep the state for a long time. And that is currently not possible with any of the technologies that are used or tested currently. So this requires something that is called error correction. There are different approaches to this error correction. There are different experiments. There are different ideas. It's very active domain of research, but it's the forecast is for the next 10 years, we would not be able really to see those large-scale fault-tolerant quantum computers. Talking about quantum computing is just one part of different quantum technologies. Quantum communications. Probably you have heard about testing of satellite quantum communications in China. Well, this is already the reality. This is maybe the most mature quantum technology, if we are not talking about quantum sensing, because quantum sensing exists already in the form of atomic clocks since a long time. But quantum communications is already something where companies are producing devices. What is the problem is that quantum communications are safe just a limited distance, 100 kilometers. If you have long distance communication, then you need to convert this quantum state into classical state and reconvert, and then to send it further. But this is a weak point. So there is a active research being done now in figuring out how to create some kind of quantum repeaters so that the states are protected also when these photons travel and when they arrived after 100 kilometers to their temporary destination. Quantum sensing is also very interesting. So there are a lot of companies investing and seeing promising results in this technology. I mentioned atomic clocks, but there is also gravimeters measuring gravitation, accelerometers for spectroscopy used in medicine. So a lot of things that we will be able to do using quantum phenomena and quantum devices. Quantum computing, I have already mentioned. And now, well, the question is what is actually used for the quantum computers? Quantum theory was based on behavior of electrons and photons. Currently, do we use photons and electrons? Well, in some cases, yes. But the most success actually was we were able to make using superconducting qubits. They are circuits, electrical circuits, cooled down to very cold temperature, where they behave in a different way than what a normal circuit behaves in a normal temperature. So, and then we can change the state. We can put these qubits, how we call them, in a superposition state. We can entangle the states of two qubits by just simple wire resonance, using the resonance between them. We can control them, we can measure them. So they are ideal, actually. The problem is that they are short-lived. The state lasts only a very short time. Trapped ions, it's a different approach. Ions, you know what it is. I mean, atom, where you take one electron and then the charge state is it's changed. So why they are trapped? Because we want to fix them. So they are kept into vacuum, and then lasers are used actually to control the state, to put them into entanglement, to move them. So they are also very interesting technologies. So I would say that these two superconducting qubits and trapped ions currently, they're very promising. Well, maybe some companies, they have preference for superconducting qubits, but it is still early to say which technology will win. There is a lot of experiments with photonic systems and other things here. Topological qubits, Microsoft invested a lot of efforts since a long time in these topological qubits. There is theoretical progress in that, but still no practical results. We'll see, ideally, if these topological qubits will materialize. That would be maybe the best option of all, but still it is very far away. Application domains, what can we do with quantum computers? Well, there are some very interesting potential use cases in material science, quantum chemistry, where we can simulate the behavior of molecules and how they react with other molecules. Currently, scientists, they can't do much except testing, well, just in the lab, but that's a very slow process. If they want to use some mathematical models to simulate it, they have to approximate. And I spoke with a researcher who was complaining about that when he uses 3 different methods, he gets 3 completely different results. And then when he's writing a research paper, so he has to just use intuition to say which one is better. So the current methods, and also including supercomputers, they have limits. And this is a very promising area on how to simulate molecules, their interactions for quantum chemistry, in innovation in pharmaceutical industry, or materials, new materials simply. Optimizations, simulations, it means that we can generate some random numbers, random probability distributions, and that is very important in some cases. This is what can't be done classically. And so we see that there is a lot of interest by banks, for example, that are setting up their own teams, doing research and looking for partners who can help them, and also investing in being partner of a technology company for the quantum platform. Quantum machine learning is also one very interesting area. It's very active nowadays. Initially, there was support vector machines algorithm that could be accelerated with quantum computer, but there is a lot of experimentation with other forms of deep learning, reinforcement learning, etc. Impact on security, or as I have mentioned, well, it can break public key infrastructure, RSA, encryption algorithm. It can also eventually break Bitcoin's protocol, ECDSA, but it can be also used for Bitcoin mining. So you can imagine that in the future, if some miners, they have small quantum computers to use for that they would outperform the others and earn money. You would probably wonder what should we do? Do we have a reason for concern about this impact on security? Well, I would say there are some companies, for example, they produce airplane engines. So the life cycle of airplane engine is very long. So it takes a long time, 10 years to design an airplane engine, to produce it. And then when airplane engine is being installed and airplanes are flying, so the companies, they want to be able to operate these engines for 20, 30 years. And nowadays, these airplane engines, they are being monitored from the ground. So, and you don't want somebody to interfere to hack your airplane engine and start bringing these airplanes from the sky down. So the companies producing these airplane engines, they are wondering if they are monitoring communication with the airplane engines up in the sky, they are safe. And they need also to be able to identify if this is their chipsets, they are capable of really supporting quantum safe encryption algorithms. So this is very important domain, for example, because the lifespan is really going beyond what is forecasted for when quantum computers will be available. Other domains, like if you are banks that are keeping their data for a long time, if this data in 10 or 15 years is no longer relevant, so you don't have time, you don't have actually reason for concern. But if this data, even after 15 years, is important to keep confidential, so in that case, you need to think about these quantum safe algorithms already now. There are companies developing this, and there are different proposals for the security, but well, this topic goes beyond now this discussion. Quantum annealers, you will probably hear about this company D-Wave that has 5,600 qubits. This is not a real computer. This you can't code it, you can't program it, except for optimization. So they are just doing the optimization, one purpose computer. So we don't suggest actually spending a lot of time on these algorithms or on these computers. Go for gate-based quantum computers that are being developed by most of other manufacturers. So what is interesting also that I met some companies that produce digital annealers, so they simulate this quantum annealer. So and then like Fujitsu, for example, they have behind it, they have a strong computer, then they install some libraries and they can simulate what this D-Wave can do. Quantum industry. So talking about what is happening in the world, I think it is very important to know where we are. So a lot of investment recently. Most of these countries here, they have very comprehensive programs for development of quantum computing. Most of the companies, incumbent and startup companies, they are coming from US. Canada is very focused. They have a lot of startup companies as well. For example, this D-Wave comes from Canada, not only them. Very good research and education, a lot of investment in that field. UK as well. I mentioned Oxford. Well, Oxford is still very much present in that, but not only them. It's really a lot of things. Especially they leverage their finance community in London that are very much interested in the finance aspects of quantum computing and what can be done there. So Germany, European Union and Germany, they invest a lot of money. We are talking about billions. China is even higher, so they invest $2 billion per year in quantum computing. So where are they comparing to US or other Western countries? They are more advanced in quantum communications, but they are not so advanced in quantum computers. Even though we can't say that they very low level of their development there, but because we know that, for example, Alibaba, they have 11 qubit machine, that other large companies, they are also developing quantum platforms and quantum software. Their government invests really a lot, and they have a lot of brilliant scientists there. Their research is really also on high level. Most of the patents, for example, now are coming from China. So they are progressing very quickly. But still, there is these investments in different countries like US, Canada, UK, Germany. It's like a new arms race. So European Union didn't do well with adoption and development of artificial intelligence. They lost that game. So they don't want to lose this one. So that is why really there is more attention and more focus now on quantum computing than it was several years ago on artificial intelligence. Japan as well, they're developing all different platforms. Other smaller countries are also very interesting. For example, Netherlands, they have very great, really strategy, national strategy on how to develop quantum computing, relying on government investment, on business companies, and on academia. So 3 pillars. And well, they have also several research centers and universities responsible for different aspects of quantum computing and quantum technologies, for hardware and for software and for applied algorithms. And they have a hub to coordinate all that. So it's really, they don't invest so much like some other countries, but they are investing enough to leverage on what they have already built during the last 10, 15 years. Switzerland is also a small country, rich country, but not really able to compete with other players here, like you can see above. But well, I will mention that because I live here. Here in Geneva, for example, there is a company that already since 15 years are developing and promoting already quantum safe communication devices. They are selling this, so they have implemented already for different banks. Quantum key distribution devices, but also quantum safe communications. We have CERN. So I posted some time ago a link to their new education series, because CERN is very much interested in how quantum computers can help them to go through the next round of experiments. So they will have huge amount of data that can't be processed with any of classical traditional computers. So they are looking parallel through different technologies, and quantum is one of them, and they're very seriously studying what can be done there. Have teams that they are already very strong in this area. Then we have ITU, for example. It's a telecommunications union. They have launched last year different working and standard groups talking about safe quantum communications. So it is very open. Actually, they twice per year they organize meetings in different countries, and the idea is actually to agree on a set of quantum safe algorithms, encryption algorithms. So it is a very difficult job, because there is a lot of proposals, but eventually it has to be, one has to be, or not one, but a number has to be selected there. India, I've read recently that also India is investing $1 billion of dollars in quantum computing, and Indians really, they are leveraging on their deep skills in computer science. So you will see a lot of people from India, great people, great talents, who are present in really a lot of quantum events. We had a summer school, and maybe 30–40% of all participants, they were from India. So they are really very much interested in learning quantum computing, especially from the software point of view. So what is needed to develop quantum industry? So I have learned actually that there are 4 pillars, very important pillars for developing quantum industry in any country. First of all, hardware platform. I will come back to this point. Scientific research and education. So this is definitely the most important, but not the only thing. So business infrastructure. If we are not able to develop and stimulate some startup companies, people, professionals who see what can be done with this and who have the ideas how to implement it, well, then, well, there is no really practical use, and everything remains just a theoretical discussion. And hub for collaboration. Well, that is a hub to exchange the ideas, to bring people together. But more important than that, only that is international collaboration. So to find partners, to see what is happening in other countries. Without that, especially small countries will have really a lot of problems. So hardware platform. Last year, I was thinking, well, okay, well, one country should focus on something that is if you don't have means, well, you focus on something that you can do. To develop a hardware platform, especially now that we don't know, nobody knows what platform will win in the end, is expensive. You need to develop several platforms in order to hedge your risks, to be able to know that what you are developing will in the end work. And that is expensive. That is really takes a long time. You need to have teams working on that. You need to have support, you need to have materials. And I was thinking, well, okay, it is expensive, so well, why not doing something that is cheaper that people can do? But I mentioned, I mean, a lot of developers in the world who are trying to do the same. So the problem is actually that nowadays you can learn quantum algorithms on your laptop. Your laptop can support up to 20, 25, 30 qubits. So you can learn basic algorithms on your laptop, on your simulator. It is not a problem. You can develop an algorithm, you can develop an application and run it on your laptop. And if you have a server, for example, very strong server, then you can simulate it. You can run this and test it on up to 40 qubits, 42, 3 qubits, not more than that. So when large companies develop computers with 200, 300, 1,000, 5,000, 10,000 qubits, and they start charging you for connecting to their platforms, then if the price is high, you won't have the access. And then the gap between developed nations and nations that don't have this means will increase. So currently, there is no gap. So you can do what Google can do. You can do on your laptop or on a server what other companies can do. But in 3-5 years, there is going to be a big gap. And that is a problem. I don't have a solution now, a recipe, what can be done there to reduce that. I will think about it. So, but in any case, I think that this international collaboration is the key. So, yeah, well, that is latest market data. There are different studies, actually very interesting studies that I've read this study recently from November this year, last year. Already 38% of companies from developed nations, they are larger companies, they are experimenting with quantum computers, and 4% developing their own applications. So in just 3 years, they think that they will have already plans and strategic roadmaps for quantum computing. So what they complain is the costs of quantum computing, that this will slow down or prevent them from maybe going through their ideal use cases. So you can search for this report afterwards. There is another very interesting study talking about what is happening in this industry, or latest research. So investments are growing 80% per year. So really a lot. 90% of all investments are hardware manufacturers. Well, not a lot of companies are doing this really. It takes a lot of money to do it. So large companies to do it, or companies funded by government funds. But mostly, most newly founded startups are software algorithm developers. That is very interesting. So let me just conclude this part by giving a couple of recommendations. So as you have mentioned, you have seen, actually, I talked about NISQ era for the next 3 to 5 years, and large-scale fault-tolerant computers in the future. So that is what we need to distinguish, really, these two parts, because not all things can be done even after 3 years. So what my recommendation is to individuals or professionals or general public is teach your children. This is very important for the future. Familiarize yourself what it is, how it will work. And if you are interested professionally, well, look at what is happening, look at these different domains, these different pillars, find what your target place would be in all that ecosystem, in all that quantum landscape, and learn, start learning as soon as possible. To business organizations, first of all, learn what this impact will have in your industry. Select partners, that is very important, because it is very difficult, very complex, and hard to learn quantum computing. Educate your executives, those people who decide on the budgets, on money, on sponsoring. So they need to know what the benefit will be, and they need to know that companies, they have to start early, not to be late, because you can't just watch, what is happening, and then when things are, it's like watching Bitcoin. So, so when it is 30,000, well, or 40,000, so if you want to buy, well, good luck. But yeah, it is important to start early. To academia, programs, interdisciplinary programs, they are really very important. This is not just a quantum physics. This is not just electrical engineering. It is not only mathematics. It is not only computer science. It is all together. And I'm dreaming of seeing some specialization program in Serbia, or some masters organized and provided by different schools together. To investors, well, think long term. That is very important, but also diversify across different hardware approaches and software, because currently it's not really known for what this will bring. Any questions there, or should I go quickly through my slides?
Hello. So far we have two questions, and I would like to thank Radić. I don't know what is the name, but first one was regarded to the quantum communication, and the question was, do Chinese quantum communication use integration? Sorry. Integration. Yeah, sorry.
Do Chinese use
quantum communication use integration?
Integration.
Yeah.
Well, they use basically the phenomena of quantum physics that doesn't allow any interference into the communication. So this is done while exchanging the encryption keys. So, when we are exchanging encryption keys, if somebody is listening to this communication, well, they can just capture these packets of the data, and then they can analyze or try to break those codes, and to be able to identify what we are talking about. Since they want to use satellite communications, this exchange of keys is vulnerable. So if somebody is also listening for this stream that is being exchanged between the terrestrial and satellite stations, then they can eventually capture the data and be able to decrypt the data that is being, the communication that is being being exchanged. So this is a very known benefit of quantum computing, that it is not easy really to understand. I can't unfortunately go through that now, but there is a lot of resources on the internet how this works. So I would advise to search for this quantum teleportation or super dense coding. These examples are really very interesting, how you can send the information from one space to another, from one point to another with less efforts. And while you're learning about this, well, actually you will realize that it is very difficult to break this key exchange.
Okay, thank you. And the second question was, which training do you suggest to follow in a communication field?
Which
training
in quantum communications? I must admit I'm not really an expert for quantum communications. There are quite a lot, I'm sure about that. So I will do some research and maybe post in our group later. I don't have a particular recommendation for that. For the quantum communications at the moment.
Okay. Does anybody else has okay, I can see the Delia is asking how much quantum programming is dependent on math and physics knowledge.
Quite a lot on linear algebra. Even more on understanding of underlying problem that you want to resolve, that you need to represent mathematically, but which is independent from quantum computing. So when you approach a hard problem, then you need to be able to understand it mathematically, to represent it mathematically. That is very important. And then this mathematical model you will translate into the model that can be coded onto quantum computers. So that is where you have also this layer of linear algebra understanding on relatively superficial level quantum mechanics. So on that level, you still don't need really a lot of knowledge about quantum mechanics. As I mentioned, if you want to innovate, if you want to develop your own algorithms, if you want to adapt them, so then you need to understand how they work, and then you will get even deeper into the math and quantum mechanics. Quantum mechanics is a mathematical framework to explain the behavior of quantum phenomena. So is that part of physics? Well, yes, but it is a mathematical part of physics. So you will not be expected to understand, for example, the oscillations or things related really to electrical circuits if you're using superquadratic qubits, so that you don't need. But there is a part of quantum physics called quantum mechanics, which is very mathematical, that if you want to develop your own algorithms or to adapt the existing advanced algorithms, you need to understand it. If you want just to use them, then you need certain skills in linear algebra and also to be able to represent your problem that you want to resolve in a mathematical way.
Okay, I have one question also for you, and it's regarding your slide, basically the part of slide that you said that 38% of the companies are big tech companies are expected to invest in the quantum QC. And for me personally, I think that was a pretty large number, to be honest. So because like now we can testify that this quantum computing is just in its beginning, and for sure why it's 4%, because in this part we are dealing with the bridge, connecting the bridge between theory and practical application of quantum computing. So basically, what do you think that is the reasoning, the main reasoning behind this? For me, I don't know, high number, and maybe for you it's not the high number, but can you just maybe give your perspective on this number, maybe a bit?
As I mentioned, these are companies from US, UK, Germany, I don't know what other country, and they are large companies. So they have heard about quantum computers. Quantum computers are available. IBM quantum computers are available for everyone. So they are curious, and they have, it is cheap, I mean, to test it. You just spend 1 week, 2 weeks to see what it is. There are a lot of online programs for free available to learn about that. So I think that's quite a reasonable estimate. So I know that they are not going deep into that. So some developers, they got a recommendation from their management to take a look what it is, write a short summary, short report. They provide the feedback. What is interesting is now what will happen with that. So are these companies really going to launch a real team, a task force, or a project to identify what really can be done with it? We are receiving a lot of inquiries from different companies, we at IBM, and we see that more and more companies that are interested. So it's not only the largest banks, for example, JP Morgan, Barclay. It's now smaller banks are coming to us. I mean, smaller, they're still medium-sized companies. They are small banks, medium-sized companies, they are coming to us. And they are still at the beginning. So they don't know what it is. We need to explain, we need to guide them through all that. Our business now at IBM is, we have a full stack. So we are developing the platform. We are developing the software. We are also developing the applied algorithms for different domains. So we have also consultants who are working together with customers. We have research labs. So some customers, for example, they launch their own research program, and then we support them with our own research scientists to work together jointly with them on a joint research program. And we have, that's the team where I'm working in, is pre-sales consultants responsible to guide companies to understand what it is, what it can be used for, to identify the use cases, and then to help them to decide on what kind of budget they need, or what time horizon they should plan for, and how they should structure their roadmap, how they should develop their roadmap for the future. So, as I mentioned, we see the interest more and more, but I also agree with this insight that a lot of companies, they're still reluctant. They say, well, okay, that's expensive, it's long-term. Should we really get on board now, or maybe we should wait 2023 to see how this will look like then? So, yeah. By the way, do you see my slides? Is that correct?
Yeah, we can see.
Okay, so I can go forward. This is how it looks like inside one of these quantum data centers, or how we can call it. So this is our CEO on the left-hand side. He used to work in research. Now he's well, on the business side. And the guy sitting on this box there is the head of research. So what we want to say by this, well, we need both research and business. That's the way how we should think about developing quantum computing, quantum industry. Well, we are talking about GPUs, about supercomputers, about accelerating computations, about deep learning, about amazing things that we were able to develop recently. So there are still some intractable problems. Why do we talk about quantum computing? Well, it turns out that there are a lot. A lot of companies actually, they responded to that survey that I talked about by saying that around 30% of all their projects that they have launched, they abandoned them because of high computation intensity required to resolve it. So they couldn't do it. They don't have hardware needed to resolve these problems. So many problems, they are just put aside. We can't do it. We need supercomputers. Even for supercomputers, we can't do it. So then just they are forgotten. So that is something that that is important for the development of the science, of technology, of the society. And that is something that will change with quantum computers. You can imagine already new materials simulated with quantum computers that are much better than the others. So that will definitely be very interesting for economic development. Logistics, how to feed more and more people on Earth. So a lot of problems, they can't be resolved currently, energy, etc. But what can be resolved, what can't? So quantum computers can't address everything. They are not a magic box that you can magic stick or something like that. It can help in resolving all these intractable problems. But a subset can be done. What this subset is a very broad and difficult question. It requires very good knowledge of computational complexity. This is theoretical science because a lot of things to learn from, and well, you can approach it theoretically and then, well, spend a lot of time understanding what it is and what complexity classes can be addressed with quantum computers, what cannot. Well, we just decided to approximate it here and to say, well, there are certain problems that we can address with quantum computers and where we see quantum advantage. I mentioned briefly the simulation, quantum systems, artificial intelligence, optimization, Monte Carlo. This is the also Monte Carlo is a technique used for as well for simulating different processes. So different, we can imagine different categories of use cases. Where are we now? Well, if we are talking about 50, 60 qubits, then we can imagine, well, okay, it's like a computer in before the Second World War, like having a dozen of capacitors or transistors, and that's very primitive. So it will take 60 years, 50 years to really come to the level where classical computers are now. But and also I would say it is similar because we see two ladies on the left-hand side and also two ladies on the right-hand side. But there is a big difference because those computers from 1944, they were not interconnected. And these quantum computers, they are interconnected. So the development, the progress is happening much faster than it used to be earlier. We have realized that actually quantum volume as a metric of how we measure the progress of quantum computers is following some kind of similar pattern like Moore's observation, where every 2 years, every 18 months, the computation capacity is doubling. So in case of quantum computers, we decided not to rely only on number of qubits. Number of qubits is important, but the quality of these qubits is also important. How long they can keep the states, how reliable the operations are. If you apply a gate and then the result is wrong, so even if you have 1,000 qubits, that doesn't help. So the quality of these qubits need also to be to improve and to be satisfying, acceptable. And the third factor in calculating quantum volume is how many of these qubits can be interconnected, because you want to entangle them, you want to bring them together. So to be able to simultaneously run quantum gates or quantum instructions on the whole system. So you want to entangle these as more qubits as possible, but wiring the qubits is challenging because they produce noise, they can interfere with each other. So that is why it is difficult to manufacture fault-tolerant computer, large-scale computer. The progress is happening slowly. Measuring this quantum volume, we have actually noticed that in the last 2-3 years, we are going even above this Moore's observation. So just last year, we had quantum volume of 64 that we have achieved with a new quantum computer. This is what I have mentioned. It's not just a number of qubits, but also their interconnectedness, their quality, etc. Not only quantum volume of 64, but 128 was produced last year, the end of last year. So we are quite optimistic about what can be achieved in several years. So, and then the target is actually set for 2023, where we will see new family, what we call new family of IBM Quantum systems that we will be able to use for practical problems. So it means applications, it means serious applications. And then, of course, beyond that, well, hopefully that we'll be able to scale and go into much more qubits. So inside this superconducting qubit chip, so here what you can see is the view under the microscope. They are not microscopic. Actually, you can see these elements also with your naked eye, but they are small. So this, what you can see, these squared things here, this one, they are qubits. The size is about 1 millimeter or so. And they are circuits. So they are able to keep the quantum state. And through these resonators, which are just the wires, we are able to control them and to read their state. Control them, it means to change the state from 0 to 1, to bring them into superposition, which is a linear combination of two different states, 0 and 1, with different probabilities of, in the end, when we measure collapsing to 0 or to 1. Some of these qubits, they are connected with other. For example, you see that this one is connected with this wire with this qubit. So that is where they can talk to each other in the sense that they can get entangled. Entanglement is a state where two qubits, they're perfectly correlated. So when you apply some operations on one, well, the other will miraculously also follow the same behavior. When you measure one and then you see, oh, this is now 0, well, you know that the other one will be also 0 or 1, depending on which type of correlation you have. So this is how it looks like. And I mentioned, well, a lot of different states, 0, 1. Well, in a classical computation, we can, what is 0 and what is 1? Well, if you look physically, bit physically is a capacitor. So it contains a lot of electrons, or it is empty of these electrons. So if it is empty, then the state of this capacitor, well, basically memory cell, is 0. If you charge it, it means if you load it with 10 to the power of 12 electrons, it will keep the information of bit 1. So you can have only 0 or 1. You can't have both at the same time. So quantum bit or qubit physically can also be in a state that represents a linear combination of these two. When we measure this qubit, then the state will collapse and be 0 or 1. But before we measure it, it will keep this superposition state. So superposition allows us to encode into quantum computing 2 to the power of n different bits of information, different states. So if you have 100 qubits, 2 to the power of 100, which is a very large number. So these are different phenomena that we are using in quantum computing, mentioned superposition, measurement, entanglement, and the basis of quantum computing. They are quantum gates, where basically we we run the gates to change the state, to shape it to correspond to the problem that we want to model, and then we want to evolve the system, this quantum system, towards a solution, exploiting interference. I think that this terminology is already complex. I realize that it requires some dedicated time to talk more about each of them and how we exploit it in quantum algorithms. But these are the basic building blocks, and this is what, for example, if you want to learn quantum computing, what you need to understand. They are not so difficult to understand, but this is what is necessary. If you want to do quantum algorithms, you need to know these things, what they mean and how they are being used in different quantum algorithms. This is a way how we can represent the state of a complex quantum system. There are different techniques to visualize this complex state. We are talking about block sphere. This is Q sphere, because block sphere, it can represent the state of one qubit. But then if you have several qubits, how do you do that? How do you visualize the state? Do you use several block spheres? Well, you can, but then if you entangle two qubits one with another, well, you no longer are able to use block sphere, that simple block sphere, to represent the state of it. So there are different techniques how these states can be visualized. And there is another very interesting thing how, for example, and I know that Ljubomir Budinsky will talk about Deutsch-Joza and Grover's algorithm. I don't know when exactly. I think it will be announced at the end. And then you will be able to go through all these things in more details, and with the idea to understand how that works. This is just an illustration how, for example, Grover algorithm works. So in the beginning, we bring the quantum states in a superposition, entanglement, all these states, they are equal. Well, applying different rotation gates, we are evolving the system towards the measured state that will actually disclose the state that we want to point out to. So Grover algorithms is used for database search of unsorted databases. If you have unsorted large database, well, it takes a long time to find a particular element because you don't have index. So you can just randomly or systematically from the first one until the end go through each element and then check if this is desired element. Well, Grover's algorithm is using quantum states representing these elements, and then going through iterations of increasing the probability using interference to find that marked element or desired element that you want to find. So that is, for example, one of the cases where a quantum computer has an advantage over classical computers. I mentioned using superposition to encode the information, and how actually this is where quantum computers can do things that classical can't. So you just imagine how this grows with the number of qubits. So for quantum state can be represented with 2 qubits. Well, 8 can be represented simultaneously with 3 qubits, etc. So yeah, well, that is maybe you will say, okay, well, great. I mean, we can then take a very large database and dump it on the quantum computer, and then we can process all that. Well, that is actually what I wanted to say already in the beginning, that not all problems can be resolved with quantum computers. Encoding large databases of petabytes or exabytes of data, taking these data and encoding in the quantum computer will take a long time. So that is not really a good use case for quantum computers. The best use case is where the solution space of that problem, complex problem, is growing as you are going through your algorithm. So the solution space will grow out of your problem, not that the data you take from somewhere and then you want to encode it into a quantum computer. And the problems where the solution space is very large and increases with the number of branching factors, they're quite a lot. And this is where quantum computers and different algorithms can provide the advantage, and they are perfectly suited for such problems. Our quantum computer, as I mentioned, this is a superconducting circuit. How it looks like? Well, we have this refrigerator. It cools down these circuits to 15 millikelvins. It's very close to absolute zero. Just in order to cool down everything to this temperature, it takes 48 hours. And also to bring it back to the room temperature, it takes a long time. So usually these kind of interventions where you need to replace something, well, they are done rarely. They are auto-calibrated. So basically, we have measurement equipment that is checking how they work and what is the frequency of these micropulses that are used to control. Everything is done in this very cold temperature, but we have some regular maintenance procedures, either online or offline. This is how it looks like within this cooling, this refrigerator, as I called it. You have a lot of wires, and you have a lot of actually golden elements here, because gold is excellent thermal conductor, and we need it because of difference in temperatures between different layers. So different layers, they will have they will sit in different temperatures. Here the qubit is and the quantum superconducting qubits, they are here, and you see a lot of loops everywhere. There are loops because when you cool the equipment to very low temperature, then the dimensions will change. So in order to prevent that these wires, they just get pulled out of their sockets, so these loops are helping to prevent that. So here you see the cage for the future Condor computer with 1000 qubits. It has been built already, so it is under development. It takes time to make sure that the design is correct, that we test everything, all those qubits, how they react with each other, how we control them. So it will take, as I mentioned, 2 years more until 2023. So different quantum computers, when they are superconducting qubits, they are connected in different way. So you need to know this topology, how you can use them. So for example, you see here in this 53 qubit device that this qubit 0 can be entangled with qubit 1, but it can't be entangled directly with qubit 2. So your algorithm has to follow this topology. But of course, we have transpilers. So your algorithm, you can develop it and then run it through the transpiler, and then this will optimize it based on the underlying hardware platform. So there is also the first commercial system that has been delivered to our customer. It is a research institute in Germany. So IBM is not only providing the access to technology or developing hardware platforms, but also doing other things like research. We have 2 research institutes in Zurich and in Yorktown, that's close to New York, providing training, skill development to our customers and to broader community. Regularly, we organize IBM Quantum challenges and summer schools. There was one in July. And by the way, all that material is freely available. Textbooks, Qiskit textbooks and video labs from that summer school. And what we are selling actually is a membership to Quantum Network. So as I have mentioned, you can access these small computers, 5-qubit machines for free. There is a queue. So when you submit your job, you will have probably to wait a bit. But for those companies that want to try larger computers and also to benefit from our professional support, we have a membership in Quantum Network that allows these organizations to advance faster with quantum computers. So as this is one of rare systems where you can really work on quantum computers for free, there is really a lot of interest in that. So a lot of people who are connecting to this simulator, not to this only simulators, but real quantum computers on a daily basis. How this works, this collaboration within the Quantum Network. For example, there is a research paper published by IBM Research talking about how to use a quantum algorithm or a new way of resolving some theoretical problems. Well, then this is published in Nature or Archive website. Then other scientists, they take this method and they test it, they enrich it, they adjust it, they invent something new, and then, basically one of our clients within Quantum Network, they will recognize, oh, well, this is interesting, we can apply it in our particular case. So then we work together with them. It's kind of collaboration work where we test these new methods on their particular use case together with JP Morgan. And in the end, things are in many cases being open sourced for everybody to use it. So you see here quite a lot of members of this Quantum Network, 132 members. Some of them, they are large companies. Some of them, they are startup companies. Well, when I say startup, well, they are serious startup, like Rahko, for example, or like Zapata. So these are people who are really leaders in their fields. Cambridge Quantum Computing, they should be also on this list. I can't find them now. There is quite a lot of universities actually, so they are also on this list, and we work with them together. So IBM focuses on some leading markets. In this round, we work very closely with Germany, with Japan. There are some plans to expand this list of priority markets to additional countries, but that's something that we'll see in the next few years. Some use cases and how, for example, for different customers, we can apply quantum algorithms, quantum circuits for different purposes. This is energy. And this is also energy for Daimler, but electrical batteries and things like that. Yeah, this is the link. Well, I'm sure that you can find it very easily when you Google it. Qiskit, well, I don't have time, unfortunately, to show you how it works. Well, maybe for the next round. As a Qiskit Advocate, I mean, I'm doing regularly these courses in Qiskit, so where I guide the people to understand how to use them, and how to program, and how to code using Qiskit. So Qiskit is a quantum information science kit. That's what it means, Qiskit. And it is actually a framework using Python. So you install libraries, and you can use it and code on your laptop using your laptop as the local simulator. Or you can connect to the backend and run your algorithm on a quantum computer with your account. So it is quite easy to learn, quite easy to use. I mean, this interface, because it's Python. This is very good source for learning Qiskit. And I like this comparison between traditional quantum computation course and what we offer, because before quantum computers, quantum information science was very advanced, very well developed, but existed theoretically. And if you want to learn using this traditional approach, well, first you are going through really a very strict education, understanding the basics of linear algebra, quantum mechanics, and then you're going through different quantum algorithms of different complexity in order in the end to come to, well, what you can do with it, how you can implement it. Well, now the approach is changing because there is a lot of people who want to test it, and because the quantum computers now exist. So instead of spending 6 months or 1 year learning the basics, quantum mechanics and quantum algorithms, and only then coding, you can do this process in a more agile way. So you can learn about very simple things using how you code using Qiskit, test it, run it, and then you go iteratively learning more things, going back when needed to quantum mechanics, to linear algebra, to understand high complexity algorithms. And that is a more practical approach. I like it, and that this textbook is based on that approach. And of course, when you start learning more and more, you can also contribute to the open source community. Qiskit is also community, and eventually you can also become a Qiskit advocate, like a lot of others who are part of the community, who exchange the information, have the access to the latest knowledge sources, and who can also be visible in that community as experts. So follow, I mean, I really invite you to check from time to time our meetup group site, where whenever I see that there is something really interesting for people to learn quantum computing, I post it. I invite you also, when you learn about something useful for the others to do it. I mean, that's part of how we can learn from each other and develop in this exciting field. Okay, well, with that, I think I'm at the end. If there are questions, I will take them with pleasure.
Hello, Saša, thank you for your excellent presentation and your talk about this. We have a few questions. One of the question is from the public, and it's how to become a Qiskit advocate. Are there already some advocates from Serbia, beside you, of course?
Okay, well,
you're not from Serbia. You're originated from Serbia. Yeah, from Switzerland, of course. But
yes, well, I have not seen. So I didn't see any Qiskit or Qiskit advocate from Serbia. well, how to become a Qiskit advocate? Learn Qiskit. And there is I think there are different rounds of application to become a member of this community. You will get a test. When I was doing my test, I thought, well, okay, it's a test, 28 questions, so I'll do it. I mean, it's not a problem. Well, it took me the whole weekend. It took me 2 days. I was really working on these problems for maybe 8 hours per day. So it took really long. So it is a good test, but it requires solid knowledge of quantum computing and how to resolve problems with quantum algorithms. So it is not impossible, I mean, to do it. So, but start learning, start developing, start testing. You need to understand Shor's algorithm, Grover's algorithm, Deutsch-Joe's algorithm, and not only that. I mean, but when you learn these algorithms, and if you understand them well, you will have enough knowledge to be able to understand also some other questions from the test. I don't have that test now. I don't remember it anymore, but I remember it took me quite a long time. It requires quite good knowledge of it. So okay. If you don't have any experience, I mean, with quantum, if you're just a beginner, it will take some time. You know, my personal motivation for that was, well, I was very active in machine learning, and I said, well, I would like to learn how to use quantum computers to accelerate machine learning. So I set a target, well, it would take me 3 months, 6 months to understand enough. Well, it was very optimistic. So I just realized it's completely different. So it has nothing to do with machine learning or with those concepts of artificial intelligence. I realized that I would like to understand how it works on physical level. So what does it mean, all these phenomena? What do we use for? Why do we use these superconducting qubits? How did they work? So then I started really learning a lot of things that it was difficult to understand. I mean, if you don't have a really background in physics and quantum physics, it's not easy. So I started learning, reading doctoral dissertations. I've read 10 of them. I've read maybe 30, 40 different research papers, important research papers, maybe 5 different books of that. So it took time until I told myself, well, this is a great field. But I think that it will take me even more time to learn about all those fields that I mentioned, like computational complexity, really to have a very good insights of quantum mechanics, of how to use these mathematical models, to explain these quantum algorithms better. So learning doesn't end. So I'm happy where I am now with this knowledge, of course. But as you learn more, you realize there's so many questions and fields to discover. And especially still, I mean, I'm still very much excited by the combination of quantum computing with optimizations. Well, now I realize it's not only machine learning, but also optimizations and machine learning. So if you are young, I mean, if you have 25, 30 years, I'm 50, but I like learning. So, but if you're young, I mean, I suggest really considering some formal education, going into this field, doing PhD, but deciding where to go, which way to go, which way you are interested. Quantum communications or quantum hardware, which we have seen a lot of things remain to be done in quantum hardware to develop a stable platform for future large-scale computer, or you want to learn and explore and practice some software sides. Software and algorithms are difficult to develop. Maybe every 2 years there is a new algorithm, even though there is a lot of efforts and a lot of great minds are working on that, but not easy to really develop. you know, when we are talking the hardware currently it has 50, 60 qubits. You know, this hardware will grow in the number of qubits as well. So those algorithms that are developed to run, that you can test them on 5 qubits, on 10 qubits, well, you can scale them. You can scale them to 1,000 qubits, of course. You can scale them to 10,000 qubits. But I expect somebody to invent new algorithms with the help of artificial intelligence, with the help of machine learning, deep learning, and all these things, because one mind cannot figure out how one algorithm's unique algorithm that can exploit 1,000 qubits, how it would look like. That is something that I'm excited to see, and that would be a real, completely new step in development of human science and technology. When we are able not just to scale up, I mean, to use, well, that's easy, but also to develop some new, more capable machines, and then to figure out how to use them. So that is going to be a real progress and still empty and open field.
Okay, I have one question regarding because I was very excited when you said that let's say the time frame is set up for 2023, that we can already see the full benefits. Let's say full benefits. Of course, when we have a stronger machine, it will even be larger. But we could see the real power of quantum computers in the hand. So basically, my question is: this was when this time frame was set up, before or after this COVID situation? And the second question to that is this situation happening right now can delay these plans for some time or something like that? If you have any.
I don't think it is really delaying, because at the beginning of pandemic, I was wondering, well, this will slow down everything. But then I just got surprised by this news of quantum volume 64 and then 128, and a first commercial computer that is being assembled and delivered to the customer, and also the machine with 63 or 64 qubits developed and made available this year. So it didn't slow down. The estimate of 2023 was made, I think, just before the launch of that larger computer.
Okay, this sounds like a promising news, to be honest. Like, because I was thinking about if this can influence this. Also, Ilya asked, can we expect that soon? When we can expect that we will have a qubit stable over a prolonged period of time, and that they are suitable for storing quantum information?
Well, two questions in one. So first, when qubits will be stable enough, that's actually the second stage. That's what I was talking 10 years or so. So when they are able really to keep that information a long time, to make it possible to run deep circuits, well, that will be another revolution. So already now we are talking about second quantum revolution. You know, the first quantum revolution being what was invented 100 years ago, and now having second quantum revolution, when we have really this fault-tolerant computers, which means that they are stable enough, but also the operations that we apply on these qubits, they are reliable. So that would mean that we have achieved the goal in development of quantum computers. Now it is too early to talk about it. During the last 15 years, there was the increase of coherence, I think 1 million times. In the first quantum computer, it kept the state coherent for nanoseconds, several nanoseconds. Now it is able to keep for 70 microseconds to 100 microseconds. But the operations actually of quantum circuit gates, they became shorter. So you can run several hundred of gates. As soon as you start applying two qubit gates that use one gate to control use one qubit to control the other qubit, to put them in entanglement or to perform operations on several qubits at the same time, they start requiring more time, like 20, 30, 40 nanoseconds. So it increases the time needed for quantum gates and shortens the time that you have available for your quantum algorithm. That is why we are talking about hybrid algorithms, where you run one short sequence on quantum computer, you take the output, and then you feed it back, well, after some processing optimization. And then this is the way how you can, you will be in 2023, or, well, hopefully that we will be able to announce great news then, that you will be able to do it. Of course, for those who have the access to this machine, surely. So the second question, how to store the data? No answer to that. There were some ideas, but we didn't see any progress there. People are working on that. They have different conceptual ideas how to do it. Maybe it will come with new platform. Maybe these nitrogen vacancy-centered diamonds, they can be used for that, because then you can use photonic systems for computation, and then at one moment, well, you can use these photons to target those qubits within the diamonds that can store the information, and then they can store it for a long time. So this is one concept, but still very much early to talk about if that will be of practical use.
Okay. Thank you, Saša, for your information. And I think that this was very insightful and very helpful to everyone. I also like to thank you, of course, for presentation. I would like to thank your attendees for joining us at this very first meetup for this year, 2021. What I would like to announce from the side of the organizers is that we are having big plans in 2021 as well. After we started with this chapter in 2020, soon we will have one meeting inside of this small, let's say, group that is behind this whole initiative. So we will define our actions in the next 3 and 6 months. So basically, we will announce to everyone what we are planning in the next period. What we can promise from our side, that we'll do our best to grow our ecosystem, to give you more interesting meetups and presentations, but as well some additional content that will be helpful and that will give you a better insight of what is already happening and how to jump into the train of becoming an active part of quantum ecosystem, not only in Serbia but also worldwide. So thank you all for joining us, and have a nice time until the next meetup. So
okay. From my side also, thank you all for spending your evening with me here, learning about this exciting field. Good luck in the future. Well, for those who would like, feel free to connect with me on LinkedIn, and looking forward to talking with you more about this or other subjects.
Okay. Thank you all. Ilija, može seći.